So today, or this evening, our order for speakers is Terrance Naidoo. Terrance Naidoo is our LexisNexis CTO. He comes with many, many years of experience. He's extremely innovative. He pushes machine learning hard, involved in natural language processing, deep learning, and all that awesome stuff. And then we'll have Amira. Amira is a master's candidate, amongst many, many other things. Runs startups and has been involved in a lot of projects. And then we have Andrew. So Andrew's a seasoned data scientist. He's got his own consultancy firm. So we'll end with Andrew, and then we can wrap up the evening. Hopefully some networking afterwards. All right. Okay. So Terrance, you up? So you can use that mouse if you want.
Okay. Great, Craig. Thanks a lot. Okay, need to get this mic sorted out first. Okay, just about the bio, like in terms of what Craig said. So yes, deep learning, all that stuff, but it's more the ideas, and Craig and the team in the back are the ones that actually execute on it. So I'll take no credit there. Okay, so I thought just with this Durban AI meetup, I mean, lots of you, firstly the response is great, so that's really cool. But I thought let's just kick it off in the right way, in terms of what's the intention of AI and machine learning is, like, etc. So one of the things which I wanted just to say is that for myself personally, it is just, I feel it's like such a privilege for us to be born during this age. It's a privilege, and like you find such a big sort of honor for us to know that we are at this cusp of changing the world. Us techies here, we took something as simple as ones and zeros, we stacked them up, and we lined them up, and we made them clever. And that gave birth to what we're calling now the AI and the machine learning, etc. So, like for me, it's AI is about what can we do with society, and you find how can we make this a better place. And that's all it is for me. There is good AI and there's bad AI. So I want to make sure that we're kicking off Durban in the right spirit, is that we're building good AI. And LexisNexis here at the moment, which I'll tell you about, our core and our mission is actually advancing the rule of law. So every single thing we do and every action we take is about how do we make society a better place. So it's just a little bit about LexisNexis. We are a big international company. Our customers we serve are in 173 countries. And we have something like 30,000 employees worldwide. So yeah, I mean, it's a big sizable business. So in terms of revenue perspective, to give you an idea, from the group itself, which is RELX, that's about 7.9 billion pounds in terms of revenue. And the LexisNexis branch of it, which is us, we deliver, like you find across the globe, about 1.6 billion pounds. So it's quite significant, and there's a huge amount of investment going in worldwide in terms of AI and how do we make society better. Okay. So in terms of Lexis here, which is local, we broke the division or the company into 3 different divisions. The first being our legal solutions. In our legal sector, what we do is we have mammoths of data, which is unstructured data, which is case law, legislation, etc. We taking that data and we really applying different techniques of AI, from natural language processing into knowledge graphs, into cognitive learning, etc. So question is, why are we doing this? We want to make our lawyers in the country make better decisions. If they make better decisions, they can uphold the rule of law, you find, far better. And you know the crisis we're facing now. It is massive. So we think we need to continue that. We need to be the bedrock, because we are the #1 market leader when it comes to legal content. Okay? The next pillar we have, we call data solutions. And in data solutions, what we have is all the government databases, from the property database to SIPC database to home affairs, etc. We take this data, we aggregate it. We're using knowledge graphs, etc., where we're finding relationships and we're finding conflicts of interest. So what we do with this, we advise companies which pay for the subscription for us, where there's potential fraud taking place in the business. And I shouldn't be saying this, but one customer, and I wouldn't mention the customer's name, the minute we put the system on, On the very first day, it went on like a Christmas tree. Boom, 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 in terms of all the conflicts of interest taking place. And what's really cool about the tech, it identifies a person to a relationship like your wife, that you might have sold a property, which is a vendor of this company, and you're a vendor, etc. It brings all of these so-called relationships together. So I think for us, in terms of upholding the rule of law, once again, we are like, in fact, meeting the sort of cause of ours, which is advancing the rule of law. And our third division brings these two different divisions together, and it's around workflow solutions. So how do we go about taking what we've done in legal research and you find sort of from our data, marrying them together and automating this in a very effective and seamless workflow where it's automated and the integrity of the transaction is there. The future for this business, we see it being on blockchain in terms of how do we pass transactions across so that we have the integrity intact. Okay, so that's a little bit about Lexis. So we do have a very big mandate that our CEO has set for us, and we're trying to make sure that that takes place. And we have a vision which I'd like to take you through, which is from now till 2030, and maybe that will help you formulate for your businesses what strategies you need to evolve in terms of your day-to-day business requirements. Okay. So I'm going to look here because I didn't memorize it. So if you look at our journey, what we're looking at is the most important thing here is what I see in the future, which is 2030 and beyond. It's not about how much of knowledge a person has, but rather about the question you ask. You need to ask the right question. So we're going to have all these fancy big data lakes. We're going to have the computing power, etc., etc. And we will be able to massage data like in such a fashion that you don't need to go and do research. You just ask a question. And it's about the person that asks the right question. So you could ask a question like, I need to go from here to the moon. And something will be built there for you. But the question is, how are you going to get there? You might have, it's like an AI machine that will probably develop like a catapult, string you on and shoot you across. But you want to get there in comfort, in safety, in style, etc. So it's asking that right question. And what we see as the evolution is, firstly we start, I'm going to try and speak a bit louder. You've got research. And currently what you have is, most of the systems we have today are geared around research. You look at wikis, you look at Google, etc. It's all about research. You go in, you type in a keyword, you type in a phrase, and it gives you back a result. Has it really helped you? Google is definitely getting there. If you look at Google now, you go, what is the weather, what is the time, share price of X, definition of this, it's almost there. So, but it's not asking the next sort of level of question. Okay? So there has to be some sort of evolution that happens. And the next part we see as practical guidance. Now what practical guidance is, it's going and taking you through a step-by-step process. So we still haven't yet hit the maturity of AI per se. Then you come to document automation. Now document automation is about creating a contract or whatever it might be, and how do you workflow this through the entire system or the legal landscape per se. Smart contracts is going to be the future. So how do we make sure that without having a centralized place that a contract is actually executed? You heard of Ethereum, blockchain, etc. That's where the future is going. So we will mobilize ourselves per se. The next is automated workflows. But it's not just a workflow that you know where like hit a click and data moves from point A to B. It's about making smart decisions within the actual workflow. And it's not just somebody pre-configuring, but having some intelligence behind it that drives it in the right direction. Okay? And then you've got SaaS offerings. I really think this is going to be the future. So at the moment, you find there's different business models. You have B2B, where you have a business to business, right? But I think B2C is going to be huge, where people like us and to the services that people like you will develop with those first four legs is going to enable the consumer to interact directly with yourself by building these actual platforms. So what does this mean there? So what it means is that the future, I see it with AI and machine learning, which is getting more evolved. The generalist job will go. And this is where you get into becoming an expert. So there's a huge opportunity for all businesses to start working on the practical guidance, the workflows, and the automation that you can offer clients a B2C option. So for example, if you wanted to complete a lease contract, how would you go about doing that? Normally you would go to a lawyer. But a lease contract is actually fairly straightforward. You could build a platform that does that for you. So there's various of these services I see will be coming out in the future, where whether you're doing your accounting for your firm or you're doing some sort of contractual negotiations, you want to purchase something, everything is going to be playing off the SaaS environment, but more from a B2C perspective. Okay, big data. So now in the first 4 sections, what's happened is that you've automated workflows, you've got the data, you understand how people are working within your system with the workflows, because you will be recording those actual behaviors. So taking all of this and dumping it in, like into a data lake, okay? And in terms of the data lake, you're going to see trends, patterns, and behaviors. It's not just about that data. It's about giving him the actual answer. It's about predicting what his next step is going to be. So you need to be so intuitive with the system that as the person is actually working with it, you unfolding insights and answers about what is his next move. Because if you don't do that, you will lose that client because somebody else is going to do it. Then once you've got the data and you understand behavior and you sort of build some sort of model to say, well, I kind of know. Now you're ready for prediction. How do you go about actually performing a so-called prediction? One of our goals here at Lexis is we want to at some point, and it's a bit difficult at the moment, I must admit, is how do we predict the outcome of a case? So you go to a system and you punch in all these values. It needs to have a reference point and it needs to give you a probability or a so-called decision of how this case will actually go. It's like how the case will actually happen in court and what's going to actually unfold, okay? So that's your probability and your prediction there. And finally, what we see is a hosted AI sort of legal service. So you will have a legal bot. You will go to a lawyer and your lawyer will be a virtual assistant, helping you through a process like how to finish some sort of contractual obligation. Okay, so that's the vision of LexisNexis. So, and that's the steps that we see. But I do see in terms of this whole graph here, it's very common steps that most businesses will have to follow. And at the end of it, it's about a crystal ball. You will go to this crystal ball, you will ask it a question, and it's going to give you an answer. And that's coming quicker and quicker. I mean, at first I thought this would be in like 2040. But as you start looking at the different tech that's coming out, I think it's going to happen sooner and sooner. And I think this is not very far away. I would give it 6, 7, 8 years tops, that most things in your environment, you'll be able to ask a question, and it's going to give you an answer. I mean, I've heard some of the research papers. You just watch me for time, huh? 'Cause okay, cool. So like the one which I read was quite cool. It was there's a system that's scanning all these images of people. You know, when you go into those CAT scan sort of devices, it's got records of hundreds and hundreds and thousands of these actual images. What it's done is that it's tracked the people that have been scanned from day one all the way to whatever it is, and they had some maybe cancerous, whatever it is. This system was able to identify in new people at a very early age, when that first pixel was distorted, just the one pixel, to say there is a common trend here, and this person has a probability of X. Now that is game changing. So that's what I'm talking about, is using this tech to say, how can we make it better for us? How can we uplift society, and how can we make our lives easier for us, our children, and our children's children? Because if we don't follow the right path, I think we're going to be in big trouble later. And I don't want to use this example, but I will use it, is if you look at, when you think of democracy, I think we've lost it. We've lost our democratic right. And why have we lost it? It's because of things like social media, with the profiling that's taking place. So you are now, and we all are being targeted. We're targeted with certain messages that are coming across, and hence you're being influenced. We saw what happened with the Trump administration and the influence that had on the election results. So we have the technology and the capabilities now, and we are starting to change the world in ways we could never do before. So for me, it's like we've got to do this in the right spirit of it and use it in the right way to do good for mankind. This is the first Durban AI meetup, so I thought it's important I say that, because I can see how the different approaches and actually tracks are like evolving as you hear the stories come out. So all I can do is humbly applaud you to say, just be on the right track, don't pick the wrong one. But anyway, back to AI. So how's it changing our industry? So I spoke to you earlier and I said that what we see is all the general jobs gone. And I think we all have come to accept that. So for you and us that have kids, we need to get them into more of the creative jobs, etc. Where if it's a creative job, it's difficult for machine learning to take over. So hence, any sort of administration job, being a doctor, I think is a problem in the future. Being an engineer is a problem in the future. So we need to find different things for our kids. Okay, but I want to show you some videos now, which really impressed upon me in terms of how fast AI is moving. It is here today. So Craig, you said you're going to help me with this for the second one, right? Cool.
Conditions in Eastern Cape State hospitals to a world first by a South African surgeon. A successful transplant of tiny 3D printed middle ear bones is set to give new hope to many patients suffering from hearing loss. A world first, a South African doctor and his team at the forefront of a pioneering middle ear transplant.
The baby's in the place. There we are. This is what we've been trying to do.
And it went perfectly.
A little bit challenging, but at least went perfect.
After 10 years of research, University of Pretoria academic Professor Mashudu Shifularu and his team performed the world's first middle ear transplant using 3D printing.
Okay, so that's bloody impressive, right? So there's, well, the end of the video shows you the guy can actually hear. So that's amazing. But if I had to unpack that, well, the research, I will give him all the credit, it took him 10 years. But I think it took him 10 years because at that time, the technology probably wasn't there. He was able to go and have this 3D sort of middle ear printed out. Where can you imagine the amount of technical experts he would have had to had prior to 3D printing? You need an engineer, you need a design person. Yeah, you're taking a picture, print it, let's see if it fits, and then you go for it. So had we had the tech earlier, this would have been, but now you're going to see a whole lot of new stuff. The fact that you could do that, I think it's going to inspire lots of people to start doing like some really clever stuff and sort of help us in terms of our health, if I could put it that way, right? And the next video is quite cool because I blended two. So I've joined the dots here where you've got one which is about a sports article, and the other is actually quite an interesting one, which you can help me.
Conditions in Eastern Cape State.
The future of TV news could look like this.
With Golden Globe winner Jennifer Garner.
The voice, computer-generated, sounds still very artificial, but the text looks far more natural. But believe it or not, no human being was involved in the making of this movie review. It was entirely written and read by machine. Scary, yes, especially if you're a journalist. Suddenly discovering a robot could take your job. So we went to meet the two brains behind this fiendish plan, two professors at Northern University in Illinois.
You know, Chris and I don't see ourselves as antagonistic to journalists.
We start to feel better until we discover that none of this is science fiction. Chris Malcolm works for a real TV network specialised in college sports. The day before we visited them, they had started to publish on their website the first stories totally produced by Larry and Chris's machine.
That's all information that you would find in a game story that any human being would write. This came faster, and it came cleaner, and it came much more effectively.
The machine took statistics from the game and out of it wrote a report, little dry but as worthy as any published by real sports reporters. After sports, Larry and Chris are going into financial and market stories, also a data-heavy field where numbers can be translated into text. And that's only the beginning.
The machine is going to cover those areas where human journalists aren't covering them, either because of manpower issues or financial issues or audience issues. I mean, no one's going to write a story. No traditional journalist is going to write a story that's going to be read by 100 people. But if the machine is there, it can write that story, and those 100 people will be happy.
Still not really reassured, we step out of the lab and across the street to a symbol of old-fashioned journalism, the Chicago Tribune Tower. And here, surprise, robot journalists are not always seen as enemies.
If a machine can take your place, then it must not have been that hard in the first place.
Here, like in any newsroom in the world, journalists are trying to imagine their jobs in the 21st century, and robots might have a role.
What they're doing, in fact, might be great for human journalists, right? Because they're going to spend the time on the things that matter, you know, investigative reporting.
In its long history, the Tribune has won 25 Pulitzer Prizes, a feat that no robot journalist will ever achieve. Or will they?
Okay, so we have Rian here, which he heads up our RPA division, which stands for the, yeah. So, but what his main coin word is for all the staff is that he's going to take the bot out of you. So that's a classic example there where what can we do to make the experience and the quality of a person's working experience here by really getting the value out. And I think the value is that bringing your intelligence into the office and not your bot, because there's far too many people doing the same processes every single day. So let's take that away and let's get you to work far better, okay? And one more video, sorry. This is not too long.
Hallå Sverige, mitt namn är Rickard, ett virtuellt sportankare, skapat efter Rickard Grönborg, förbundskapten. Mitt namn är Rickard, ett virtuellt sportankare, skapat efter Rickard Grönborg. Dygnet runt under hela hockey-VM kommer jag finnas här för att ge er det senaste från turneringen. Hockey-VM kommer jag sända live för att lära er allt ni behöver veta om hockey-VM i Slovakien.
President Juan Carlos Varela, along with ministers, is attending the expo, joined by a delegation of union representatives.
Slovakien.
I 2 veckor?
Ja, det stämmer.
Och prata hockey?
Men snälla Rickard, nu pratar jag.
Otroligt.
Okay, so with the first video you saw the articles were being written and somebody created that tech. And the second video, you got somebody that's mastered the art of taking like a human face and actually perform the action. So what's going to happen now is that as we start developing these sort of APIs / microservices, etc., we're going to start joining the dots. So my piece of advice to all of you, just watch the news articles, watch what's out there, keep yourself abreast of what's going on, because there's so many small changes that are happening that could be quite big and quite impactful to you and your businesses and yourself going forward. And my last words, please promise me, good AI, no bad AI. We need to move in the right direction. Thanks a lot.
Cool. Okay. Yeah, so I don't like using mics because they end up standing here and pointing to things and explaining numbers and words and stuff a lot, so I hope that's okay. And if you can't hear me, just raise your hand and I'll project more. Yeah, so firstly, thanks to Craig and LexisNexis for taking this initiative of doing this whole AI meetup. I think it's awesome. In Joburg and Cape Town, like the machine learning and AI communities are already quite established, and I was quite surprised to see that we don't have something going here in Durban. So this is really awesome to build a community of people interested in things like machine learning, AI, and so on. And I kind of was presumptuous in thinking that the other two speakers will do an introduction to machine learning and AI, so I would switch it up and do something different. And what I'm speaking about today is, so it's basically a light introduction to quantum computing. And I'll explain what that is, and, well actually, firstly, who's heard of quantum computing here in this room? Okay, so quite a lot of people, and hopefully you guys will learn a little bit from this presentation, and if you have any questions, let's keep it interactive, stop me and let's chat about it. Yeah, so before I dive into the content, I just want to mention a few of the things that I'm affiliated with. So the first is a company called LearnML, stands for Learn Machine Learning. And this is centered around machine learning education and training in South Africa. So myself and Francesco Petrotigi, he's one of the pro-vice chancellors at UKZN, we found ourselves often getting approached by individuals and corporates to educate them on parts of machine learning techniques. And so we decided to come together and actually formalize this and like put together courses for people to take. So you can find out more about it on the website, and also if you're interested in becoming an educator, just drop me a message. And then I am a part of the UKZN Quantum Research Group. Hey Maria! I'm currently doing my master's there, so Craig so kindly introduced me as a master's candidate, and it's not as fancy as it sounds. But I'm doing research in quantum machine learning, and I'll explain a little bit what that is later on. But our research group is also doing other very cool things in quantum physics. So they're researching like the dynamics of open quantum systems, quantum teleportation. Now that sounds fancy. And we're actually funding for students, for master's positions and PhD programs. So if you guys are interested, and that's something that interests you, like drop me a message. And then last but not least, the Deep Learning in Java X. I just mentioned this briefly here because, so the main Deep Learning in Java is this really big conference that happens once a year somewhere in Africa. This year it's in Kenya and Nairobi. And it's an amazing opportunity to network with other researchers in the field and other people in industry to see who's doing what in machine learning and AI. And it's very much about strengthening and upskilling people on the African continent. And an offshoot from this conference is the Deep Learning in Java X, South Africa, which happens here locally in South Africa. And if you're interested in applying for next year's event, keep an eye on that website. I'll put all these slides up on the Meetup group, so you'll have access to them. And yeah, so I was an organizer for that event this year, and it was really, really awesome. Okay, cool. So now we can start with the content. And if I'm blocking you, okay, cool. So just a quick recap as to classical computing, right? And when I say classical computing, think about the laptops you use, your daily PCs, all that kind of stuff. That's what I mean by classical computer. And at its basic form, we can store information, I think Terrance even mentioned it, in bits, right? In state 0 and state 1. And I'm going to call these states. So you can have information around bits that exist in state 0 or in state 1. And you can have these bits manipulated in a circuit, which is exactly what happens on your computer, by passing them through what we call logic gates. And all logic gates are simple calculations or rules that tells a computer how to process a bit, right? So it tells you to do something given some sort of scenario. So if you guys can't see at the back there, but this is an example of an AND gate, right? So what this mathematical rule says, if the first two bits are both in state 1, so if bit B and bit A are in state 1, then you flip the third bit, which is bit X here, to 1. Otherwise, it stays in its original state of state 0. So that's just a very simple example of how you can manipulate information in a classical circuit, right? And now in quantum computing, you have totally the same analogous version where you can store information in state 0s and in state 1s. And we call these things qubits, quantum bits, right? Quantum bits of information, with one difference. In quantum computing, you also have an additional state called a state of superposition. And I denote this state of superposition by the symbol here, that's phi, that's called phi. And you can think about the state of superposition. So mathematically, all it is it's a linear combination of states 0 and 1. So it's like, it can be written like this, it's something times 0 plus something times 1, right? But intuitively, how you can think about this superposition state is it's actually a probabilistic state. So what superposition represents is when you actually measure it, when you actually look at it, the state collapses to either 0 or 1. So this superposition state is in either 0 or in 1, okay? And how we write these quantum states, or these quantum bits, is we just represent it by this weird notation. So these angular brackets and these pipes are called Dirac notation. That's just to say that this is a quantum bit of information. It's a qubit. And in fact, these coefficients here, this alpha and beta, gives us information about how likely a qubit is in state 0 or in state 1. Okay, so they kind of correspond to like how likely is the superposition state in state 0 or in state 1. And the squares of these numbers, the absolute squares of these numbers, correspond directly to probabilities. So alpha squared here is the direct probability of how likely superposition state is in state 0. And beta squared represents how likely the superposition state is in state 1. Okay, so that's all superposition is. It's nothing spooky like Einstein said. And yeah, so it's really just like this linear combination of two states. And then when we measure it, we have like either 0 or 1. And we call these coefficients probability amplitudes in quantum mechanics. Okay, so they're not direct probabilities, but they're probability amplitudes. And so now, the only constraint on these coefficients is that their squares have to sum to 1. Okay, so that's the only mathematical constraint about these coefficients on a state of superposition. And this is interesting because you can start to notice that alpha and beta can then be anything, right? They can be negative numbers, they can be complex numbers, they can be real. And this is the crucial difference to what makes it different to a classical computer, which you can make probabilistic. And I'll explain what I mean by that. So imagine you have your normal computer, and you say, I've got a bit of information, and I want to make it probabilistic. So I want to say that its next state will be state 0 with 50% chance, or state 1 with 50% chance. Or state 0 with 70% chance, state 1 with 30% chance, right? You make it probabilistic. That's making a classical computer probabilistic. But when you do that, you only have the real line to work with. You only have real numbers from 0 to 1 in which you can manipulate those probabilities, right? And so you only have this kind of linear straight line function, which can represent the probabilities of these states. And that's the crucial difference between a classical probabilistic computer and a quantum computer, because in a quantum computer, you can now think of the state of superposition phi as taking on points on a sphere. So this is called a block sphere. Don't worry too much about what you're seeing here, but you can just see like the state 0 is up here, state 1 is down here, and any other point on the sphere represents an arbitrary state of superposition. And that's kind of like, that's the main difference here, is that you have more to play with in terms of how you think of probabilities and probability amplitudes. And so, of course, now, if you have information that can exist in another state, in a different state, you'll also have different ways to process it. So in quantum computing, this gives rise to different logic gates, different rules in which we can process this information on the computer. And I just mentioned this very briefly here because it really annoys me when like the Avengers and Ant-Man and all of these people talk about quantum physics, and it's like, it's really not how it works. But so quantum entanglement is something that also comes up and makes quantum computing a little bit different. So in a classical circuit, you have bits of information that can't really interact with each other, right? But in a quantum circuit, in a quantum computer, when qubits are in states of superposition, they can start to interfere with each other and create correlations that are so tightly correlated that you can't observe these types of correlations in a classical setting, so outside of quantum physics. And that's things like quantum entanglement and interference, which is different from a classical computer. So we have superposition and we have entanglement and interference in quantum computer that makes it different from a classical computer. Okay, cool. Everyone okay so far? Okay, great. So now the next question, well, probably the second most common question I get asked after what is quantum machine learning is how are these computers built? And I'd like to just disclaim that I am in no way an experimental physicist or a hardware person at all, so I'll try and do this justice, but I focus on the software, so forgive me if I don't have all the answers to your questions about this, but I'll try to do it justice. But also one thing I'd like to point out is that it's still very, very early in the game, right, in the space. And many different companies are trying different ways to build quantum computers. So how a quantum computer, a fully fledged quantum computer actually looks in 20 or 30 years' time could actually be completely new to the ones we're seeing today. So some of the major companies in the space, you'll recognize a lot of these guys, but there are many, many more, by the way, many more companies doing research in the space, how to build a quantum computer. In fact, there's startups coming up every day trying to build quantum computers. But I just mentioned a few here. And the number you see below these companies is the number of qubits they have in their quantum computer, right? So your mind is probably instantly wondering, wow, D-Wave, what are they doing right to have 2,000 qubits and like be way ahead of the game? But there's a small caveat to D-Wave's quantum computer. So it's a very unique and specific architecture. So it isn't like a general purpose quantum computer that you can use for anything. It's for a very specific problem that arises in physics. So small caveat to having 2,000 qubits, you can't really use it for a lot of things. And then some of the companies don't have numbers under their names. That's because they're still building their quantum computers, right? And so these companies here, Google, IBM, and the likes, have experienced a lot of success in building a quantum computer. And how they do it is they have built this superconducting quantum computer. And all that is imagine you have pairs of electrons, right? They're called Cooper pairs. And you cool these electrons down to super, super low temperatures. And when you do that, then you start to observe these weird quantum properties of these particles. So that's when you can start to harness them and use them in computation. But cooling something down to absolute zero temperature is not an easy thing to do. So that's why when you see pictures of quantum computers right now, they like take up all these big rooms, and it just illustrates how early we are in the game because we don't have it figured out yet. So that's one of the problems with that type of method. And then this company called IonQ came about. They have 79 working qubits, and they actually have the highest accuracy on these qubits. So these qubits are still very noisy, it's still very early, can't really process them very well. But IonQ have the highest accuracy on their qubits, and how their quantum computer is built is, imagine you have now charged particles, right? So charged ions. And they trap these ions in free space using electromagnetic fields. So they trap them in a line, and then these ions are actually what the qubits are. They represent the qubits. And you can manipulate the states of the qubits by like shining lasers into them and changing the charge and creating these coupling effects and so on. But the problem with this quantum computer, or the potential problem, is that you can only trap ions in a line. And there's a finite number of ions that you can trap in a line. So it's unclear how this quantum computer is going to scale in the future. But who knows, they might come up with some new crazy idea and surprise us. Okay, and then the last one I want to just quickly mention here is by this company called Xanadu. So they're a startup in Canada, in Toronto. And they are building a photonic quantum computer. And this, I think, is the most intuitive one to understand. And it's really quite a cool idea. So just imagine you have a beam of light, right? So just some laser or a beam of light. And this light, imagine like you just dissect it into like pockets of light. Okay, so like, and these pockets are called photons, right? These little particles of light. And these photons are actually qubits. They're viewed as qubits. And so you can pass this light through different filters which change their polarization, which changes the state of the qubit. So you can start to create things like superposition and entanglement just by passing this ray of light, this beam of light, through the right types of filters and changing its polarization. So that's what Xanadu are doing. And now, I guess the question you should be asking is, okay, cool, very fancy and exciting, but let's say we have a quantum computer that comes around tomorrow, what can we use it for? And more specifically, I'll tie this back to like, how does this come into AI and machine learning? So there are some use cases for like the near-term quantum hardware that we have today, so the really small quantum computers, but what I'm discussing now is more for like when the real fully fledged quantum computers come about, what can we use them for? And this is directly taken off IBM's website, and they propose 4 things. So the first, which I agree with, is this idea of medicine and materials. So some chemical compounds and atomic structures are so complex that we can't even begin to analyze them on the classical computer that we have today, even the really super powerful ones, right? So it's been postulated that a quantum computer could perhaps simulate these complex chemical compounds and atomic structures. We can start analyzing them, and we can start developing things like new types of medicine and new types of material to help us in our lives. Then they also briefly talk about supply chain and logistics. So a quantum computer, in theory, should be really good at complicated optimization problems, which of course supply chain and logistics are, right? I mean, it's all about, you have a grid of transportation, transporting things, optimizing supply and demand, all these complex things that come together in a network. Perhaps a quantum computer can be good for solving a problem like that. And then this example, which I hate, but I'll mention it here because everybody wants to know what's happening in finance. Financial services, so yeah, a quantum computer, it's been argued that, so something as complex as financial markets, right, with inherent randomness, could perhaps be modeled by something like a quantum computer where randomness is also inherent in it. So perhaps you'll see new financial models, or faster transactions, or different cryptography. We definitely see different cryptography, but all of these things tie back to financial services, and perhaps quantum computers can revolutionize that industry. And then the last one, and the one that I'll be talking about now for the rest of the talk, is of course AI, artificial intelligence, and how does quantum computing and AI come together. So can a quantum computer help us in AI, and can AI help us in quantum computing and quantum information processing? And that actually leads to like this beautiful intersection. So you have quantum information processing, machine learning and AI, and this intersection, which I mentioned earlier, quantum machine learning, which is what I am trying to do my research in. And essentially what we're looking at is, we're trying to understand how can quantum computers help the classical machine learning algorithms that we have today? Can they speed them up? Can they make them better? Can we have different types of algorithms? And then on the flip side of that is like, how can classical machine learning help quantum algorithms? And can we develop like entirely new algorithms using quantum computers and classical machine learning processes together? So it's like this trade-off between the two. How do they integrate? How do they give us like a synergy? And natural questions that should arise then is, when you couple these two things together, right, is perhaps classical intractability, like maybe models that we can't solve on a classical computer can be solved on a quantum computer. Innovation, maybe we can come up with entirely new algorithms, right, using principles like superposition, quantum entanglement, quantum interference to come up with entirely new ways to do things. Computational complexity, maybe we can get exponential speed-ups in our current algorithms just by introducing the quantum computer to do something for us. And of course, like, can we actually use machine learning and quantum machine learning to prove that a quantum computer is better than a classical computer? It's not proven, by the way. So a lot of people are under this impression that a quantum computer is this supercomputer that will kick classical computers on its ass, but that's actually not, hasn't been shown. So what has been shown is that a quantum computer can do certain problems really well, like factoring large numbers, which breaks certain encryption methodologies. But that doesn't stop somebody today from writing a new algorithm that does exactly the same thing and runs on a classical computer. So it actually hasn't been proven that a quantum computer is better. Then my last 3 slides are just on this idea of quantum machine learning, because I kind of loosely defined it, and now I'll just explain a little bit more, and then I put up some resources, and then we can take some questions. So quantum machine learning can be thought of in different ways, right? Because it's this intersection of two ideas. So I'd like to just solidify what I mean. So the first example is, imagine you have a classical machine learning algorithm. So let's take a support vector machine, right? Which is something that's used quite often in machine learning. And a support vector machine says, okay, I've got a data set that's quite complicated to analyze as it is. So I transform it. So I'll map it, let's say, to higher dimensions so that it becomes easier to process. It becomes easier to cluster things or classify things. And how it does that is it applies kernel functions. Those kernel functions do that mapping for you and like calculate that similarity of data points in high dimensions, right? So kernels can actually be very computationally expensive. So they could take a very long time to run on your classical computer, on your laptop. So instead, if you just outsource a kernel to a quantum computer, you can speed up, in theory, your entire classical algorithm, your entire classical support vector machine, just by outsourcing that piece to the quantum computer, to the quantum node, but keeping everything else the same architecture. So that's one way of like combining two different things. And then there's this idea of this variational circuit. So don't worry too much about like this diagram here, but just imagine this is a quantum circuit. And this quantum circuit has parameters in it, theta, trainable parameters, like you have in a classical machine learning algorithm. And so we can use a classical machine learning architecture to optimize a quantum circuit. So we'll look at the output of the circuit and we'll minimize the cost function, just like we do in machine learning. And then we update these parameters in our quantum circuit and we keep going through this loop. And that's also an example of like quantum machine learning. And then of course, you can have both of these things together in something that we call hybrid computation, where we still have like this classical quantum loop, and in this quantum node we have this circuit, a variational circuit, which is what we call it, that depends on these parameters. So these parameters need to be optimized, and so does something else in the classical machine learning algorithm. And then there's like this whole optimization process that happens, and it's this give and take from classical quantum computing. And that's quantum machine learning kind of theoretically. Yeah, so that is it from me. And if you're interested in this kind of stuff, I have put up a ton of resources here, and I will share this on the group. But so if you're interested in quantum computing and quantum information, I would highly recommend this book by Nielsen and Fong. It's like the canonical book that you can't avoid reading. IBM have this really cool thing on their website where you can drag and drop and create quantum circuits for yourself. And you can actually execute it on their quantum machine. So it's quite cool. There's also a book on supervised learning with quantum computers, which is the integration of machine learning and quantum computing. There's an edX course on quantum machine learning that's really mathematically intense, but it's great. And then the company I mentioned in Canada, Xanadu, have developed this Python package. If you like programming, you can actually use Penny Lane to create a quantum machine learning algorithm and execute it on a quantum computer via the cloud yourself. And it's really simple and have beautiful documentation, and so I urge you to go try that. And then just 2 papers on like a classical translation for algorithms we're all familiar with, right? Like linear regression and neural networks in a quantum framework. So that's all there. And then you'll notice a name that pops up quite a lot, Schultz. That's actually Maria Schultz, and she's sitting at the back there. Sorry. So if you're interested in any of the technical details, you can chat to her over me. And she also works for the startup Xanadu. So she's like, really, I always tease her and say she's the father of quantum machine learning, but yeah. Okay, cool. So, and also, again, thanks to LexisNexis. I think next time if we do this talk, and assuming I get invited again, we'll do like a more, I think it's important also to do like practicals and introductions to machine learning and AI. If you guys are interested in that kind of stuff, then like actually maybe teaching what an algorithm does, not on a quantum computer, the classical one, like what support vector machines are, neural networks, all that kind of stuff. So yeah. Questions?
So a quick one, really?
Yeah.
What's the time frame do you think this will become real on a laptop that you will have actually?
Okay, so I assume you mean like a fully fledged quantum computer, right? Because right now you can do quantum computations on a very small one. Yeah, on your laptop, yeah. But like a fully fledged quantum computer that will come about, I don't think in my lifetime. I'm quite pessimistic. Well, actually not pessimistic. I think I'm realistic about it, and I would love for it to come about in my lifetime, but I don't know. I think the hardware problems are.
The cost is too high also. I think the cost is too high for you to understand the process right now. So just to justify the spend would be.
Yeah, and also I just think that there's just too many hardware hurdles. Like I don't know. Like I think we'll get to hundreds and thousands of qubits, but like to crack to crack like what is the algorithm? SHA-256, right? We're gonna need I think millions of working qubits, like coherent qubits, and I don't know. I just don't see that happening in the next 30, 40, 50 years. Yeah.
Have you seen the research with underwater computers and processes around quantum?
No, to keep it cool.
Yeah. So the biggest challenge at the state that it is now is the cooling.
Yeah.
And understanding how to get it managed to do the qubits transformation.
Yeah.
So now they're saying you're either going to go higher atmosphere or lower.
I know there's like all these crazy things about holding it in space.
Yeah, the space one is probably a probability. But then we have to be on Mars, obviously, to get that computation to work.
Oh God.
So that's the challenge.
Yeah.
I just want to know, so apart from the sorting algorithm, that search algorithm, the Shaw's search algorithm, what other quantum algorithms are they already existing? So what stuff is there that people have really figured out how to do a quantum computer much better than a normal crystal?
Okay, so there's Grover's search algorithm, which searches through, right? And then there's Shaw's algorithm, which does the factoring, right? So they're two separate things, although it's kind of like an extension.
Yeah.
But to answer your question as to what algorithms are there are lots. Okay, but what algorithms are better than a classical computer? Not lots. So there's like the Date-Joseph, am I pronouncing that correctly? Algorithm which like determines. So it's a very simple example. Maybe I'll explain it quickly. So imagine like you've got a sequence of numbers, zeros and ones, and you want to determine if that sequence is constant, so all ones or all zeros, or if it's balanced, like half ones and half zeros. The amount of times you have to query that sequence in a classical computer is half plus 1, right, to determine whether it's balanced at a worst case scenario. But as a quantum computer, you can do that in one call by putting these sequences into superposition and just like doing clever things. So that's an example of like the Date-Joseph algorithm, which also exists. So those three are the most popular, like they use to illustrate why quantum computers are cool and better. But yeah, I don't know, Maria?
I think it's also a bit unfair because like in classical computation, problems are very connected. Like Grover's algorithm has so many variations that it's just a common problem, so you just say it's only those three or those two. But it branches out. There's a cool website called the Quantum Algorithm Zoo. And it shows you like a lot of those.
Anyone else? Okay. Last questions? Okay.
Sorry. Do you know what Google has used or what use cases they're using there?
So they claim a lot of things, and like the way they're building their quantum computer is through a superconductor, like I mentioned in the first example, but they don't give us access to use their quantum computer. So whether it's as good as they say, or whether they have as many qubits as they say, it remains to be seen. Yeah.
Didn't Google buy D-Wave?
Did Google buy D-Wave?
One, yeah. They are part of a collaboration that have one.
Okay. Corporate stuff. Just kidding. Okay, cool. Thanks very much.
So, good evening. I'm Andrew Collier, and whereas the first two speakers were very generous to you in having very beautifully illustrated slides with zero code, I'm going to be the diametric opposite of that. Very little in the way of nice illustrations, and there'll be a bit of code. But as a little bit of a precursor, I work for this company called Exegetic Analytics, which is a virtual consulting company, and in the data science sphere, and we specialize in data augmentation, machine learning, and automated reporting. There's 7 of us kind of distributed around the country, and we have a lot of fun doing what we're doing, obviously. Also, what I'm going to be talking about this evening is not actually really ML, but it's perhaps you can think of it as a precursor to ML. In addition to those 3 things that we do, we also do quite a lot of training, and what I'm going to be showing you this evening is the first component of our Spark course, which we're in the process of sort of rehashing. So this is the beta version of Module 1 of Exegetic Analytics take on Spark, and I hope that it will at least be a little bit illuminating. So, as a bit of a prequel to this, Spark is a platform for doing big data computations, and if you've encountered the term big data, then you've probably heard about the 3 V's, which is the way that people sort of define big data. But I'm a lot more sort of pragmatic than that. If the data doesn't fit into RAM on my laptop, then it's big data. I'll tell you why. That's a perfectly reasonable thing to do, because if your data fits into RAM, then your computation is very, very fast in principle. But as soon as your data becomes too big to fit into RAM, then your operating system, which is super smart, starts paging, which means that it takes chunks of data that's in memory and puts them onto the hard disk, which effectively frees up new space for you to then occupy with more data. But the problem with this is that the process of taking data from RAM and stashing it on disk, or bringing it back from disk into RAM, is really, really slow. And consequently, as soon as you start doing this paging operation, your computations, which are in principle quite fast, suddenly grind to a halt. And the more data you feed into the system, the slower things get. So Spark is a platform for you to get around this issue. And basically the idea is that you don't just have your problem running on a single computer, you distribute it over a network of computers, right? So, and by doing this, you essentially get to leverage the RAM on each of those individual machines. Of course, there is a downside to this, because you now have to move data around on a network. But if you're smart, then you can kind of minimize the amount of network transfer that takes place, and just ensure that data sits on particular nodes, and that's where all the crunching takes place. So we've got this Spark cluster, and this kind of schematically is what you would have on the Spark cluster. So you have one or more execution nodes. So these are machines on which the actual processing is going to take place. And these are just your standard servers, right? They've got one or more CPUs and a bunch of RAM and maybe some hard disk. And they communicate with each other via a network. And then you've got a cluster manager, which essentially oversees the interaction between these individual nodes. And then importantly for you, as like the driver of your Spark cluster, you've got this driver code, which can be written in a number of languages, which I'll talk about in just a moment. But essentially what that driver does is it kicks off the operation, which is then disseminated across the cluster by the cluster manager. And then on each of the nodes in the cluster, you have tasks, which is basically a unit of work. And that work is then conducted by what's known as an executor. And normally you'd have one executor process per thread on each of these machines. So if these are 4 core machines, then you'd have 4 executor processes running. I mentioned that there are a number of different languages in which you can write that driver application. So the Spark system itself is written in Scala and Java. And I don't know anything about either of those. However, Python and Spark I feel fairly comfortable with, and that's high-level languages. I mean, Python and R at least. I spend most of my time working in R, but for the purposes of Spark, I'm a Python guy. And that's what I'm going to be showing you this evening is going to be largely, more exclusively, in fact, Python. So one final thing before we delve into the code, and that is just a comment about the actual underlying principle of how Spark works. And it actually, if you have heard of a system called Hadoop, which is kind of like typical big data system, then it relies on a technique called MapReduce. Basically, the idea with MapReduce is you have a problem, you then fling it out over a cluster of nodes, and the computation takes place there. And then you have, that's the mapping operation, right? You map onto the nodes. And then you have an operation called reduce, which basically goes and assembles all the results from the individual nodes and brings it back to you. That's your answer coming back. Now, this works really well, but in the context of Hadoop, the downside to this is that you get data being persisted to disk at multiple stages in the process, and this is what drags down your Hadoop system, and that is that transfer of data from memory onto disk that I mentioned earlier. Spark tries to circumvent this by keeping everything in RAM for as long as possible. Okay, so let's take a look at this. Right. So if you haven't seen this before, this is a Jupyter notebook, and people working with Python are very accustomed to working in a Jupyter notebook. Basically, you've got cells, you write your code in the cells, you can execute it one cell at a time, but what's also really nice about these Jupyter notebooks is that you can embed Markdown in them as well, so you can kind of mix documentation with code. So it's a very nice way of presenting your work in sort of a literate form, so that you can actually wrap text around your code and your results. Anyway, I quite like it. So we're going to kick off our interaction with Spark by loading up a couple of pretty standard Python modules, and then this find Spark module, which I'll talk about a bit later. And then we kick off our interaction with Spark by loading up the PySpark library and creating a Spark context. So this context is essentially a handle that's going to be used to communicate with Spark. Now, in this case, I haven't passed any argument across, so what Spark is going to do is it's going to take a look at the machine that I'm running Spark on and basically try and max out all possible computational capacity. So it's going to take over all four of the CPUs on my machine, and it's going to try and run processes across that. You can actually, at this stage here, specify just exactly what kind of a network you want. So this is where you would set up your connection to some sort of an external cluster. So for example, you've gone and created a cluster of machines on AWS. This is where you would initiate the connection to that cluster. Okay, now I said that this is the first module in our course on Spark, and so I'm going to be talking about a data structure which is known as an RDD. So RDD stands for Resilient Distributed Dataset, and this is kind of where Spark started, but it's not where you want to be if you're wanting to do machine learning with Spark. The reason for this is that an RDD is super flexible in the sense that it allows you to basically work with data. Earlier, I think Trevor mentioned unstructured data. Sorry, Terrance, I beg your pardon. Using an RDD, you can deal with unstructured data, so you can put text documents into it, for example. But if you're going to be doing sort of standard machine learning tasks, ideally what you want to do is take whatever data you have, unstructured or not, and put it into a table, right? Something with rows and columns. Now, Spark caters for this data frame or tabular data, but that's for the next part of what I have to talk about. So an RDD has a number of really good characteristics. Firstly, it's a collection of elements. So you're going to see in a moment that we're going to create an RDD from a vector or a list. It's immutable. So once you've created an RDD, you can't actually change it. And this has efficiency implications. It's fault tolerant. This is also super important, right? If you're dealing with a cluster of nodes, your data is distributed across those nodes. What happens if one of them dies or the network connection to it is interrupted? Spark will deal with that situation, right? It's tolerant of those kind of issues. Data can be stored across a distributed file system. Obviously, we want that if we're going to have a cluster of nodes, and can be operated in parallel. Well, that's kind of self-evident. Okay, and then finally, there are two types of things that you can do with an RDD. One is known as a transformation. So this is basically an operation that does something to your RDD and returns another one to you. And then you have an action, and actually returns a result. So you can think of this in a map reduce context. This is like a mapping, and this is a reduction step. We'll see how that works. Okay, so there are a number of ways that we can create RDDs that we're going to explore, actually just one of them. But before we actually create an RDD, it makes sense to talk about partitions. And a partition is a term for the way that your data is going to be divided up across your cluster. And I had my daughter make up this very nice illustration of paper dolls. And the idea here is this illustrates like a sequence of data, and I guess it's not readily apparent on this projector, but there are actually 3 different colors of paper dolls there. There's a purple, there's a green, and a blue. And what I'm trying to illustrate here is that you've got a whole sequence of dolls, different varieties, and they've been divided up into partitions, which are these boxes. And this is essentially what happens on your Spark cluster. You start off with a whole sequence of data elements, you push it onto the cluster, and Spark, using some fancy heuristics, decides, okay, I'm going to take this chunk of data and put it onto the first node, the next chunk put onto the second node, etc. It distributes them across the nodes in the network. And let's take a look at how this would actually happen in practice. So, starting off here by creating a list of letters which correspond to the colors of the dolls, so P for purple, G for green, and E for blue. And so there you can see the list. And now we want to get it into Spark. So we run this parallelize operation. And you'll notice that before parallelize, we've got this SC. SC is the handle that we created back here. Right? SC is the Spark context. So as I mentioned, this is the handle that we use to communicate with Spark. So we take that and we parallelize this list, and it returns a Python RDD. And at this stage, we can check on the number of partitions. 4. Why do we get 4 partitions? Well, I have a 4-core laptop. So what Spark has done is it's taken a couple of those colors and put them onto the first 4, a couple more onto the second 4, etc. We can immediately interrogate just exactly how they've been distributed as well by taking a look at the actual layout of the individual items. Don't worry about the details here for the moment, but what you can see is that the first 2, P and G, have been put onto the first node, and then we have B and P onto the second node, G and P onto the third, and then a whole bunch onto the last node. Now this looks kind of a little bit fishy, right? The fact that you've got 4 data elements on the last node and 2 on each of the other ones. So it looks like this kind of be an asymmetric distribution of data across my little mini cluster. And for sure, this is true, but the differences between the distribution of data across the nodes is exacerbated for a small data set, right? Here I've only got 10 elements. If we had hundreds or thousands of elements being distributed across the cluster, then they would be much more evenly distributed. Okay, so now that we've got one RDD in place, we can go ahead and create another one. And this time, we're just creating a sequence of integers. So the range function in Python creates a sequence. In this case, it's going to be 0 through to 9. And once again, using the parallelize function, we convert that into an RDD. And again, you can see that it has 4 partitions. And we can change the number of partitions. We're not going to delve into that at the moment. Start talking about actions. So actions, as I mentioned earlier, are things that return an actual material result. And you can see here that there are a selection of actions like first, collect, take, etc., etc. This is just a small sample of the total number of actions available on an RDD. And maybe while I'm talking about this, that the Spark documentation is really quite superb. So it's very extensive and very, very detailed with lots of examples in it. So in addition to these actions, there are many others, and it's very easy to find out a little bit about them. So just to illustrate how some of these actions would be applied. So we've got 10, which is the most recently created RDD. We apply the count action. Right? 10 was those 10 individual numbers in the list. 10 count gives us back 10. There's nothing terribly surprising about that. And then we have a couple of functions actually accessing the components of that RDD. So first, for example, returns just the first item in the list in the RDD. Collect returns all of them, which seems like a really handy thing to do. And it's a really good thing to do if you've got a small RDD. But if you've got an RDD consisting of thousands, tens of thousands, millions of elements, then trying to collect them is probably not a terribly good idea. Because what collect is doing is it's going to each of the nodes in your cluster, grabbing the data, bringing them all onto your master node, and then rendering them into your notebook. So in principle, this is an operation that could take a really long time and could give you a lot of information, most of which you really don't care about. So typically, collect is something that you do only once you distill down your RDD to just the essence of what you want to get back. Okay, we've seen how the data are partitioned, and this is once again another example of how an RDD might be split up. So we have a different RDD, and in this case, it's 2, 3, 2, 3. So you can see that the distribution of data across the 4 nodes is kind of random. It's only, but this is only because we've got a really small sampling of data. So in addition to collect, probably a more useful operation is take, where you can just extract like the first number of elements from an RDD. So here, take 5 just gives me back the first 5 elements, as opposed to collect, which gives you back literally everything in the RDB. You can also go and extract samples at random. So take sample and with an argument of true, that's replacement. So this is going to go and sample from our RDD. With replacement, though, it's take a random sample at random, write it down, put that out back in again, take 3 of them, give me back 3 elements, and if we go back and look at the distribution of data across RDDs, we've got 4, 0, and 9 back, and we see those are actually on 3 separate nodes. So effectively what this take sample is doing is it's going and randomly sampling elements from each of the nodes in your cluster. So it truly is a random sample, not just a random sample from a single node. And then you have some sort of typical mathematical operations like sum and mean. They're going to go and do things on your RDD, and of course these are only meaningful computations to apply if you have a numerical RDD. So my paper dolls RDD to calculate the sum or the mean would not be a particularly meaningful operation. Okay, so actions give us back results. A much more interesting thing in the context of Spark is the transformations, because this is where the actual compute happens. And again, there is an enormous range of possible transformations available in Spark. And we're going to talk about just a few of them, but this is just a slightly larger set of them that I'm listing here. Let's just move on and actually take a look at how some of these things work. So the first one is a mapping. And basically what a mapping does, take an RDD and apply a function to each of the elements in that RDD and then return a new one. So for example, 10 is our original RDD with the numbers 0 through 9. We're mapping onto it a function, and this is a lambda function, which in Python is a way of writing sort of a function in a very compact way. So this is a function which accepts a dummy argument x and returns the square of that number x. So what this is going to do is take this function and map it onto each of the elements in the RDD and return a new RDD. And we can then, because we want to actually see what the results look like, we call collect to give us back the results. But the interesting thing about this now is that the transformations in Spark are lazy. And that means that when you run this line, actually nothing happens. It basically just sets up an operation in a queue. And the operation is only actually applied when you then string an action onto the end. So nothing happens here. It basically says, aha, you want to perform a mapping, but I'm not going to do it right now. I'll only do it when you want the results. Here, when we collect, that's when the mapping is actually applied. So having this lazy evaluation actually also results in a whole lot of computational efficiency. on Spark, because in principle you may have a number of operations that have been applied to your RDD which can be simplified. So by delaying until you've got all of your transformations in place and then looking at possible simplifications might allow you to actually be more computationally efficient. Okay, so mapping, we can also do filtering, and the syntax here is much the same. Right? We've got our RDD that we're operating on, and we're then applying a filter method. And what filter does is it applies a function to each of the elements in the RDD. That function returns a Boolean result, either true or false, and then filter will only return to you the elements for which the function returned true. And the function in this case is taking x, the argument, doing modular division by 2, and then comparing the output to 1. So we're basically dividing through by 2 and looking at the remainder. If it's equal to 1, we get true. If it's equal to 0, false. So what this is going to do is extract only the odd elements from our RDD, and finally we collect, which means apply an action, which gives us the result back. So of those squared numbers that you can see at the top there, this operation now only gives us back the ones that are odd as required.
Andrew, do you take questions?
Yeah, I was going to ask the
Maria, yes. I'll
Okay,
take the
cool.
question.
So is now in the memory, is now the RDD muted? So you said the data set is kind of immutable, but it now got replaced by these updated sequences or not?
So
is this extra?
No, so this 10 squared RDD is not actually mutated in place. So what's going to happen here is you've got an RDD, you apply a method to it, and at that point you've now created a new RDD, because remember these are immutable objects. So you take the old one, you create a new one, and then on that new RDD you then apply this collect action. So there's never a case where you're actually mutating the RDD in place, where it's just creating a new one of the transformation.
Sorry. So like if you just go up a little bit.
Yep.
So this function now, how is that executed in terms of like, you know, you're running on 4 different ports of the laptop. So then does that execute for each partition instantaneously?
It does, exactly. So this is going to, well, not only is it executed for each partition, it's executed for each element in each partition. So each of your nodes has got a partition of the data, and then the function is applied to each of the elements in that partition on the node, right? And then when you finally run this collect operation, what happens then, that's the reduce step, where effectively Spark goes around to each of the nodes and accumulates the results from each of them and consolidates them together to form this final result for the entire cluster.
And TensorFlow does similar.
Sure. Absolutely. Because now you're changing the topic altogether.
You know, in my head I think machine learning and I think like batch, you know,
yeah.
the same thing, and then it consolidates and keeps reminding you of this.
Sure.
So, but like the benefits here is that this is quicker, because it's executed on an element level, which TensorFlow can't do. I don't know.
I know very little about TensorFlow.
Okay.
I'm afraid so.
No.
I really can't draw analogies.
Okay.
But the efficiency here really is achieved by virtue of the fact that you're spreading the computation out over multiple machines rather than trying to do it all in one place. So, yeah.
Simple question. With these if I were to map 2 functions onto a collection, so in sequence, am I right in saying it will only enumerate the collection once until I do a collect at the end?
Yeah, okay, so you can take a map operation and then another map and then a filter and then another map, etc. And you string these all together, but they're lazy, these transformations. So you can string on as many as you want. Nothing is actually going to happen until you then take an action and put an action on the end.
So I think the question is more about the efficiency, right? So if I were to do a +1 on a vector of numbers,
yes,
and do another +1 on the vector of the numbers, will it enumerate the collection once or twice?
Well, no, exactly. So the idea with the lazy evaluation is that if you have 2 operations like +1 +2, you can then take those and consolidate them into a single operation.
Pretty much like
+3, right?
Yeah.
So being able to take all of these operations, not apply them at the time that they're actually activated, delay it until you actually need the results, and then you can potentially take all of those transformations and compile them and something that's more efficient. Yes?
So it's almost compiling an execution plan for all the steps and then executing that the moment you hit collect.
Yeah, that's my understanding. Is that I mean, it's going to, once you've got all of the available transformations and you're finally applying an action, then it takes a quick look at all those transformations and tries to find the most efficient way to execute.
Yeah.
Yeah.
Cool.
Yeah. Thank you for asking questions. If there are no questions, then being up here can be an awfully lonely place, especially when people are walking out. So, okay. So, they both had dinner plans. Okay, so I'm going to skip over that and that, and let's just illustrate something that's maybe a little bit more illuminating. So. We've talked quite a bit about like how these operations can get stacked up and that they're only actually evaluated when you apply an action on the end. But in principle, this seems like a really good thing. But in practice, it can be a bad thing because if you have a chain of transformations acting on your RDD and you then put one action on the end, what's going to happen is all of those transformations will be evaluated. You'll get your result back. But now if you go and apply a new action to the end of that chain of transformations, what's going to happen is they'll all be evaluated again, right? Which means that all of that compute that went into the first series of operations will be applied once again, which is horrendously inefficient. So you have the alternative of taking your data and applying those transformations and then caching the results. And so this essentially, when you cache the results, it executes all the different stages of the transformation. So you don't really have an action at the end, but you take that RDD and you cache it. In principle to memory, but perhaps to disk. So to illustrate this, I have here a function in Python, which is probably a fairly naive function, but it basically takes some number n and evaluates whether or not it's prime. It's going to return true if it is prime and false if it's not. And just to run a simple test on this, I'm taking the isPrime function and running it on this sequence of numbers, so 1, 2, 4, 7, and 15, and the result is false, true, false, true, false, and this is because indeed 7 and 2 are prime, and the rest of them are not. Yep, that seems right. So we have a function. It's always good to know that your function. Okay, so we're going to use Spark to find out how many primes there are between 0 and 1 million. And to be honest, I don't know how long this would take using normal Python, but what we're going to do is we're going to take advantage of the fact that Spark is going to distribute this job over all 4 cores on my laptop. I'll illustrate that it is indeed doing that. So what we do here is starting off with our Spark context, we generate an RDD with this range function, and the range is going to give us the numbers between 0 and 1 million. And we then have filter, which is the transformation that we saw earlier, and we apply the isPrime function. So this is going to generate a sequence of trues and falses, depending on whether or not each of these numbers is prime. And then finally, we're going to count those, which is going to give us the number of primes. Okay. And as you can see, the answer is 78,498. And for me to actually run this, I actually need to go back and just recreate the Spark context. And now we go down here. I'm going to run that, but just to illustrate that it is indeed running across all of the cores on my machine. Top. So this is a utility. I don't know how legible this is from the back. What htop does is it just shows you the fraction of each of your CPUs and how they're utilized. So these are the 4 CPUs on my machine, and this is basically a bar plot showing the intensity of the action of each of those CPUs. And you can see at the moment my laptop is essentially just idling, and what we're going to do now is go back and count the number of primes. to it. And you can see that all 4 of the cores, very briefly, admittedly, were completely maxed out, right? And producing that result. And maybe we can make this a little bit more aggressive and go from 1 million up to 10 million. Okay, there we go. So all 4 of the cores, once again, maxed out. I don't know how long that's going to take. It could take quite a lot longer because, as I mentioned, that's a very naive function for testing primes. But okay, so while that's chugging away, let's go back to this. I think that's essentially what I wanted to talk about. So this is, I guess, just been like a very small flavor of what's possible with Spark. If I am indeed invited back again, then my plan for part 2 and part 3, maybe even part 4, is part 2 will be talking about structured data in Spark. So how you can read in a CSV file, for example, and get a nice tabular data frame. And then part 3 would be take that data frame and then actually do machine learning on it. And then part 4 would be streaming operations. So for example, if you have a stream of data flowing into your system, how you can use Spark to operate on that stream. So that's me done. If there are any other questions, I'd be happy to try and answer them.
Can we have this virtual?
Oh, sure. Yep, I'll put it on the Meetup. I'm not sure. No, I believe it's still running. Oh, no, there it is. It's done. So there is the answer. 664,000 pounds between 0 and 10 million. Go home and tell your significant other that. I have no doubt they'll be impressed. Maria.
Very quickly, the R, the
Yes.
resilience. I mean, what's the difference here to like any like parallelization? There's probably a little bit more theory behind it. Because you said, like you mentioned briefly, that actually even if that node crashes or connectivity is lost, you still can work with the data, which I assume doesn't mean that the data is reproduced somewhere.
To be honest, I'm not exactly sure how that works because I'm a data scientist, not a data engineer. But my understanding is that it is your cluster of nodes is literally resilient. So find that data from somewhere and recover, which I think is super important, right? I mean, given the fact that networks are inherently unreliable things, you just have to have telecom internet to know that. Things are going to go down in your cluster, and you don't want to get halfway through this enormous calculation, one of the nodes goes down and everything breaks. So resiliency is a super important characteristic. Yeah, but how it works, I don't know. Looks like I'm off the hook now. So thank you.
I think the whole reason for this meetup was purely to get the Durban community together. So this isn't a LexisNexis thing, even though there's quite a bit of branding around. However, I know that Terrance is fully invested in this meetup, and we're going to support any which way we can. So if that means providing venues or speakers or whatever it is, we're there to support Durban and the AI machine learning community. So what we want to do going forward, we want to understand what sort of topics you guys are after and how we can get those speakers in and how we can build workshops and how we can sort of maybe we can branch off into other things and you guys can run with these sorts of meetups and all the rest of it. All right. So that's really the idea and the aim behind this meetup. Okay, cool. So thanks everyone.
Thank you.
Appreciate it. Thank you.